All right, guys. There's remember from last year a few things like this.
Oh God.
We're not even there yet. This is just
Video.
some of these have a sum and some of them don't. Yeah, recall this? Okay, let's just see how much you remember. Which of these have sums?
First one.
Number 4.
Okay, first one for sure.
Last one.
Okay, does anyone remember what the first one is? What is the sum?
4.
It's
4.
No, it's 4. No.
3.5.
3.75. No.
It's less than 4, but more than.
I think it's like 10.
Four.
Oh, it is 4. Okay.
Okay, so there's a formula. So you remember, guys, this is called an infinite geometric series, whose sum is given by the first term over 1 minus the ratio. Again, this is just like, this isn't really coming up now, but it is soon. Okay, but again, I just want to remind you that some sums converge, right? So we say number 1 is a convergent sum because it has a finite limit. It has a finite sum. Okay. Number 2, true or false, it converges.
Incorrect. True.
No, it does not converge. It goes on to infinity.
What is the natural log of 2?
It's about 1.
It's a fraction?
Yeah,
Sure.
it's less than 1.
It's less than 1, but greater than 0?
Yes.
So number 1 is geometric because you're multiplying every term by the same ratio, 1/2. This is geometric because you're multiplying everything by the natural log of 2. This converges because what you're multiplying by is less than 1. Recall all this stuff, guys? Okay. So 1 converges, 2 converges. Like, we're interested, I mean, we can figure out the sum too. It would just be ln2 over 1 minus ln2. It's not that interesting, but there it is. Number 3.
Not convergent.
Very good. 3 is called divergent. It's a divergent sum because it doesn't approach anything. It just flip-flops between 1 and 0 forever and ever. Okay, so we would say 3 is divergent, 1 and 2 are convergent. Now, number 4 is an interesting one. Number 4 is not geometric because you're not multiplying through by the same ratio. But what you're adding is getting smaller. You guys see that? 1 and a half, a third, a fourth, blah, blah, blah. So what do you think, convergent or divergent?
Convergent.
Okay.
Divergent.
So what's really strange about this is that number 1 and number 4, at least in my opinion, look pretty similar in terms of, like, my terms are getting smaller. This one decreases so fast that we actually say it has a sum. And in fact, number 4 has no sum. It's divergent. This is what basically the next month in this class is. And it's not intuitive. It's because, like, how would you know that that converges but that doesn't? Okay, so this is like basically what we're starting with today is this idea of how do you know whether things converge or diverge even if the terms are decreasing. I think it's pretty safe to say if this went up, like 1, 2, 3, 4, 5, divergent, like for sure, because that approaches infinity. Okay, so you can start to think about there are some conditions you need right away for it to even be potentially convergent. Okay, like your terms got to get smaller, for example. Okay, so you have to have that in mind, and now we're going to talk about convergent and divergent integrals. Okay, because really all integrals are infinite sums. That make sense? Okay, so let's look at a couple of examples. Okay, first one. Check the notation. Can someone interpret what that means? Yeah, what's that?
The area under the graph of 1 is over x squared. X equals 1 to infinity.
Right, so I can express this integral sort of like that. And isn't it basically asking you, now this is a little bit strange, but see if it makes sense. Is the area underneath that curve from 1 to infinity, is it infinite or is it finite?
Fine.
Maybe.
Oh,
That's not infinite because
no, it's gonna be infinite because when you.
But we say that sum 2 plus a half plus a fourth is finite. No, okay, so now this really is going to challenge your ideas of infinity and finite and all this stuff. Like, so this integral, in fact, is finite. Okay? So let me show you how we can figure that out. Okay? This is called an improper integral. An improper integral has a characteristic where one of your limits, or both, I could put a negative infinity here, where one or both of your limits is infinite. Okay? So this is how we take care of it. This is how we take care of it. You guys know by the fundamental theorem of calculus that you end up taking the antiderivative, plug in b, plug in a, and then subtract them. There's a problem here. Yeah, I can't plug in infinity. Okay, but you guys know by now, plugging in infinity is just taking a... Okay, so this is what we do. First step, you replace the infinity with a letter, typically t. Okay, so what we do, think about this for a second. That integral is the same as the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. Does that feel okay that those would be the same thing?
Yeah.
Yeah, right. I think it's not bad. The rest of this is just taking the integral and then taking the limit afterwards. Any guesses sometimes what happens with that limit after you take the integral? What are you going to need? L'Hopital. Okay? Sometimes. Okay, so that's why they're all sort of connected here. Number 51 on your homework, right? Yeah, sorry about that. That shouldn't have been assigned. My bad. Okay, so guys, what we do here is I'm going to work horizontally here just because I don't have a lot of room. But this is the thing that I'm going to look at when I potentially collect your homework tomorrow. Okay, is this notation. This is super easy to be lazy with. Okay, and I got your back on this, guys. This kind of sucks. It's not that hard. It's just annoying to write it all. I understand we have to do it. Okay. All right, so this is the same as the limit as t approaches infinity of the antiderivative of 1 over x squared. So what is that? Good. Negative 1 over x. Evaluated from 1 to t. Okay, so that part isn't any different. So now let's use our fundamental theorem. And so this limit as t approaches infinity is really negative 1 over t plus 1. You guys okay with that? You just plug in 1, you're subtracting it? Yeah. When you subtract the negative. So this is the point at which this problem is no longer an integral. It's just a limit. Okay, so this is where sometimes you may have to use L'Hopital, or sometimes it's pretty easy like this one. Okay, so what is that? It's just 1. So we say that the value of this integral is 1. So the area underneath that curve from 1 to infinity is 1 unit squared, if you will. Okay, pretty cool? Makes sense? So we say this integral is convergent because its limit is finite. Okay, just like the stuff you guys learned last year. Okay, so now watch. Now let's do example 2. Can I erase this? Okay, I'm going to do example 2. And check out all I'm going to do. Ready?
If this is gonna diverge.
Alright, so now we're going to do the integral of 1 over x. Same idea as this one. The graph almost looks identical. But 1 over x decays less, let's see, slower, I guess, is 1 over x squared. So if I were to sketch it, it might look something like that. Right, is that a fair assessment? Something like that? So it's like, how do you know that that one doesn't have a sum, but that one does, right? Like, it's not intuitive. Like, there's no way to, like, at this point, just look at it and be like, oh, duh. Like, I don't know. I think that's kind of tricky. Okay, well, let the calculus show you that it diverges. Okay, so let's do it. First step is what?
T.
T, good. Replace infinity with t and write your limit out. See, this is kind of annoying, right? I understand. I totally get it. Okay, keep going. Gives us the limit as t approaches infinity of the natural log of the absolute value of x. This is an instance, guys, where that absolute value is going to be really important. So make sure that you include that. Okay, so this gives us the natural log of the absolute value of t minus 0. But I wanted to show that just for emphasis. Like, I knew that was 0, and I'm sure most of you did too, but oftentimes this is not 0. Okay, that'll be like in the last problem. Like, that actually gave you the answer. So now maybe you can see, look at that. Think of the natural log graph in your head if you have trouble with that. It's that one. As t approaches infinity, what's that limit? Infinity. Okay? So because this limit is not finite, this integral we say diverges. This is a divergent integral because its limit is infinite. But I chose these two examples to start with just so you can see like how close it, like why does that one converge but that one doesn't? Like why is that the case? Yeah.
So would the answer to this problem be divergent?
Yes.
Not infinite.
That's right. Okay, so often, that's a good question what Jake brings up. Oftentimes the question will be, determine whether the following integrals are convergent or divergent. If they're convergent, find the sum. Find the limit, find the value, something like that. Okay, so this one you just say is divergent. And there's your work to support that. Okay, so now guys, let me write out the formal definition of what an improper integral is. Okay, we say that the integral from a to infinity of f of x dx is equal to the limit as t approaches infinity of the integral from a to t of f of x dx, or the integral from negative infinity to, I don't know, we call it b, of f of x dx would equal the limit. So the only difference here, guys, is what? T approaches,
Negative.
yeah, negative infinity, the integral from t to b.
But you can have.
Sure, for sure. Yep.
Which one would you let T approach then?
That's a good question. That's a really good question. So let's entertain that, guys. What if you ended up having
You just break it
this
down.
integral from negative infinity to infinity?
You do t and negative t.
You'd go from negative infinity to
Zero.
some number plus that number to infinity, and then you break it down into this case.
Can't you just do from negative t to t as t goes to infinity?
No, because then you have a negative infinity there somewhere. You have to let t approach as well. Right, you would have this case
But could
for
you
that one.
have at the bottom negative t?
Mm-mm.
Negative infinity.
So this is what's really important is this part right here, guys. We say, so I'm just going to write the first case. We say that our improper integral is convergent if the limit as t approaches infinity of a to t of f of x dx is finite. If our limit's not finite, it's divergent. Any questions so far?
So, do you, in the end, use improper integrals to evaluate like those geometric sums instead by using an integral?
You'll see. Actually, you won't. You'll be in France. But you might see.
You'll see on video.
You'll see, guys, pretty soon that this idea of convergence of an integral lends directly to the convergence of a series, sigma, or the divergence of a series. Like that's when the meat of this class happens. But you'll see. But yes, we can certainly do all that. So, guys, that's the first type of integral. That is the first type of improper integral you'll see. Ready for number 2? Okay, first of all, can someone please tell me what makes this integral improper? Take a second and look at it. This is the first time all year you've seen this. There's no infinities. Max?
Divide by 0.
With the dividing by 0?
Yeah, you guys are both right. Very good. The integrand is not continuous at 3. Okay, so there, you haven't seen that yet. So this idea, again, lends itself towards infinite or finite area as you approach that asymptote. Okay? So how do you think we take care of this case? Any idea what the next step looks like? Sam?
The limit as t approaches 3 of the integral of 0 to t of 1 over 3 minus x. Yes.
Super close.
Oh. 3
From the
minus.
Very good. There it is. So you have to be careful now. So look, we're going from 0 to 3. So we're approaching 3 from values that are less than it. Okay, so we have to approach 3 only from the left. That's the only part we're interested in. Because in fact, if you just put that function's not even defined for like 4 and 5 and 6 and stuff, for values greater than 3. Okay, so this is the second type of improper integral. It's when one of your limits makes the integrand discontinuous. But you handle it the same sort of way. Let's do it. So what do you think? Any guesses? Convergent, divergent?
Convergent. Easily.
No idea, right? Though, just by looking at it, like no idea, really. It's just a guess. So that's what I'm saying. Like it's not intuitive. Okay, that's fair. I agree.
I'm on the second version. If I'm wrong, You can kick me out.
All right, so I did this out beforehand, guys, just so we can kind of go through this pretty fast. So it's -2 root 3 minus x evaluated from 0 to t. Oops. Which is equal to the limit.
Oh, jeez.
So again, guys, I know you can do this. You guys did awesome on that integrals test. Like, this is just a u substitution integral. Okay, so if you trust me getting down to that step,
You're wrong. I could be wrong. I still don't know.
what's the answer?
Negative
Convergent.
Oh, it's like this, right?
Oh.
Sorry, my bad.
2, 3.
That's
So as we approach 3 from the left, this is a constant,
That becomes 0.
and then that part becomes 0. So our limit is equal to 2 root 3. So this is a what integral? This is a convergent integral, and we say that it's equal to 2 root 3. Okay, notation. Need all that. Let's do one more.
Guaranteed.
So this really this is like the, no pun intended, but the integration of what you learned yesterday and what we learned last unit. Right? Like, I really didn't mean.
He did it for the video.
I did it for the.
We did it for the show. Unbelievable.
So
We did it for the show. They made up that.
Okay, someone please tell me why this integral is improper.
Because
Raise your hand. Yes, Greg.
it's secant is 1 over cosine, and 1 over cosine at pi is
-1.
1 over 0.
No, but
Yeah, Nikita.
isn't it tan when you take the rule? I mean,
no.
It has tangent in it.
Oh yeah.
Has tangent, David?
Because it's undefined at one point in the.
And what point is that?
I would say when x equals pi over 2.
Okay, good. So here's another type of improper integral, guys. You have to be careful. So this function is discontinuous at a certain value between a and b. It's fine at 0, it's fine at pi, but it's not at pi over 2. Okay, there's a vertical asymptote there. So what might help you with these functions that you might not be so familiar with, like secant, natural log, cosecant, whatever, is to sketch it, if that helps you. Okay, we got that going on. Okay, so we have to break this up. Okay, any ideas how we can rewrite this integral? We got to show every step. Yeah, Alexandra.
0 to pi over 2 secant x dx plus for pi over 2 to pi secant.
Very good. So writing it like this now whittles this problem down to that last type of integral that we just did. Yeah.
well, that's gonna be 0.
Is the integral of
Oh, that is such a good question. Okay, I'm going to get there in a second. I'll just do it now.
the integral?
Yeah.
yeah.
Okay, I'm changing color. This has nothing to do with this problem. Okay, but you have to notice this. Let's look at the graph of 1 over x. Okay, if I asked you guys, what's the area under the curve from -1 to 1?
No, it's just twice there.
Something weird.
No.
Okay, so this might bother you a little bit, but remember, this is a divergent integral 1 over x. So that means that this area is infinity, or negative infinity, I guess, right? What's this area? So I'm going to put it there. Infinity minus infinity is indeterminate. It's not 0. Okay, so what Sam said is actually something that is worth mentioning. You guys know that if you take the integral from negative a to a of f of x dx equals 0, just as long as f of x is an odd function. And I mean, the above and the bottom cancel. But now you have to keep in mind that that's only valid if f is continuous. Okay, yeah, good point. Anyway, keep going here. Alright, what's the integral? Who knows it? Secant x dx. This is why I did it. Who knows it?
Oh, I know what it is.
Shout it out.
So 1, 5, 5.
Okay.
I panicked.
This has to be fast. You guys gotta know this one.
1
The natural log of secant plus tangent. Remember your Pythagorean identity, sine squared plus cos squared is 1, etc., etc. Just know secant goes with tangents. Secant and tangent go together all the time. What's the derivative of secant? Secant tangent.
Absolute value of secant.
Derivative. What's the derivative of cosecant? Negative cosecant, cotangent. Those go together. Okay, group those functions together and it helps you memorize these. Okay, the integral of secant is the natural log of the absolute value of secant plus tangent. Okay, but before we get there, we need limits.
Oh no.
Okay, so what I want you guys to do is to think about here. It's going to be the limit. Can you tell me? What is this? From the integral from 0 to t, what goes here?
Limit as
T approaches
t
pi over 2.
approaches pi over 2 on either side, doesn't matter.
It does matter. Okay, you have to make sure, guys, that when one of your limits is your discontinuous point, you're going to only approach that from one side. So if you're, look, I drew it. This might help you. From there, yeah. See how fast that was when you saw the picture. Okay, from the left of secant x dx plus the limit as t approaches infinity of.
You mean
Oh, sorry. Pi over 2.
No, just
From the right.
From the
Of
right.
T to
Good. And it's okay for you guys to use the same letter here, because this limit and this limit are like very much self-contained. You're not going to confuse the t's. Okay, any questions so far? Okay. So now we have the limit as t approaches pi over 2 from the left of the natural log of the absolute value of secant plus tangent evaluated from 0 to t plus the limit so this would be the natural log of messy, right? Not messy, but actually it's not messy, it's the opposite, but it's intimidating maybe.
Plus 10.
We're not even at the point where we take the limit yet, right? We have to use the fundamental theorem of calculus to simplify this first. Okay, so here we go. Let me try to sneak in underneath here. The limit is t approaches pi over 2 from the left of the natural log of secant t plus tangent t. Okay, now we have to sub in 0. I know, right? You got the secant of 0 plus the tangent of 0 is 1, good. The natural log of 1 is 0, so we're cool with just that.
Yay.
Yeah. Plus, secant equals 1.
Sorry, never mind.
Good. Okay, so the first step looks the same here. The natural log of secant t plus tangent t.
Wait, why don't you do pi?
Oh, I'm sorry. You're right. You're right.
What is secant pi?
Oh.
That was -1.
Okay, so let's do this together without me writing it. if you plug in pi, you get -1 plus 0. This might really mess you up if you didn't have the absolute value. Right? Because you can't take the natural log in -1. But this is that case when I told you it's really important to have that. Alright? So this is just the same as the first case where it is the natural log of just 1. Which is
0.
okay. So I can don't worry about that. So minus the integral or the limit of when we plug in t. Okay, so it's you guys care if I just put minus here?
Maybe? No. All good.
Thanks. Secant t plus tan t. Okay.
I don't know when you would ever have this, but if you had something like cosecant x plus tan x in your natural log, and you were plugging in something where in one of them it was undefined, what would you do? Like, would you ever have that, like, you plug something in and one of them's undefined?
Like when you plug in pi or something?
Yeah.
That meant that up here you would have needed to replace
Yeah,
that
but
with.
like if they were not like secant and tan, but like cosecant and tan for some reason, where like one of them was over sine and the other was over sine.
Try to come up with an example. Okay, I'm not really sure. Alright guys, let's do this. Shh. Max, thank you. Guys, what's that first limit? See how much you have to know about algebra? Like you have to know what the behavior in the natural log of secant and tangent. So that's why graphs help. So as we approach secant t, or as we approach pi over 2 of the graph of secant t from the left, we're going up to infinity. How about tangent? You guys remember that graph?
It has little things.
That's like x cubed.
Just like that?
Yeah.
Okay, so we basically are doing infinity plus infinity, which is infinity, that's fine. And then the natural log of infinity is infinity. Okay, so that first limit is infinite. And that's enough for us to stop.
What if the second
What
one?
if the other
So what?
What if the other one were too?
If the other one were...
were like minus
And there would be
two,
infinity minus
then your answer would be.
You'd be adding.
I mean.
Okay, I'm getting ahead of myself a little bit. When you add two integrals together, and if one of them is divergent, the sum is divergent automatically. So we just figure out that that one was divergent. Okay, but yeah, it's a good question because infinity minus infinity. Right. Yeah, it's a good question. But know that. Okay, let me say that again a little bit more formally. The sum of two integrals is divergent when at least one of them is divergent. That kind of makes sense, like intuitively maybe.
You can't have, they can never cancel each other out.
No, what I said is an absolute truth. Yep.
Well, because like that example you showed us, they did cancel each other out. The one where.
Right. True. It's a good point. Yeah. All right, then over here, guys, if you wanted to just complete this up.
Minus infinity. It's just minus infinity, right? No.
It's the same thing.
What you end up getting, it doesn't really matter. It's a moot point right now. But what you end up getting is this is negative infinity. Since there's a negative there.
Wait, but isn't it the absolute?
You can do it out if you want. Okay, write it out if you want to see it. Write it out, like for real. Do it,
Yeah,
I dare you.
no, I realized, but it's the inside the absolute value.
Right now.
Never mind. Never mind. It's okay. I trust you.
Thank you. Sam Shapiro making his appearance. He's got to steal the spotlight.
He knows what he's talking about.
But infinity minus.
You'll hear it, Alex.
Nikita.
So as the panel they're talking about area on video of 1 over x, the area here is the exact same as the area of y.
But there's but adding only works when things you add are finite. All the things you know about addition and subtraction break down.
Okay, so
No, wait, I have a question.
Yeah.
Going back to you.